Oh, how was that for an intro? Gotta love that tune. I've heard it 40 times now. Every time it just takes me back. The tones, the rhythm, and the crossfade as it slowly fades away and welcomes you to section 8.3. Rational functions and their graphs. Objectives, this section, that you should keep in mind. To identify properties of rational functions and to graph rational functions. There's quite a bit of vocabulary in this section. Rational function, continuous graph, discontinuous graph, point of discontinuity, removable discontinuity, and non-removable discontinuity. Throughout the videos, I will try to have those firecracker explosion type badges pop up when I discuss vocab. So that'll be a good time to take notes or take special care to remember the vocabulary and its meaning. An essential understanding. Often they're not this long. This really gets at the meat of the section, the ideas that we'll be studying in more depth. But here goes. If a function has a polynomial in its denominator, its graph has a gap at each zero. So let's take a quick second to look at what that means. And pow, we have a fraction with a polynomial denominator. So we have this polynomial in the bottom of a fraction, and we're told that the graph of this will have a gap at each zero of the polynomial that's the denominator. So what zeros are, if you recall, are the values or the inputs that will result in a zero. So in this case, x minus 6, thinking about this logically and not spending too much time on it, x would have to equal 6 because 6 minus 6 equals 0. So interestingly enough, this graph, or the graph of y equals this fraction, will have something interesting going on, some kind of gap at the value x equals 6. You'll get much more familiar with those as we move ahead. Continuing on with the essential understanding, the gap could be a one-point hole in the graph, or it could be the location of a vertical asymptote for the graph. You can get a reasonable graph for a rational function by finding all intercepts and asymptotes. So again, those will be the points where the graph crosses the x or y axis, as well as any lines, horizontal, vertical, or otherwise, that the graph gets infinitely near to, but never quite reaches. Remember, that's like the example we often use of walking halfway to the wall and then halfway to the wall. That can be repeated indefinitely, and you would never reach the wall. Very similar to asymptotes, as you'll recall. Sometimes you will also have to plot a few extra points to get a good sense of the shape of the graph. So even with those key details known, to give you some information about how to graph, you may have to plot some specific values, possibly using an x and y table, in order to come up with a very reasonable sketch of the graph. Oh, and after a brief pause, I changed slides. I was reminiscing. I wanted to hear that introduction music again. So maybe. No, we should get back to work. You use a ratio of polynomial functions to form a rational function, like y equals the binomial x plus 3 over the binomial x plus 16. A rational function, vocab word rational function, is a function that you can write in the form of f of x equals p of x over q of x. So interesting, now we're writing this function as a division of two other functions, or a ratio of two other functions, where p of x and q of x are polynomial functions. The domain of f of x is all real numbers except those values for which q of x, remember q of x is our denominator, but for which q of x equals 0. The graph of a rational function can be continuous or discontinuous. Very important terms. The graphs of 3 rational functions are shown below. First, we'll focus on the graph at the far left, a continuous graph. So take note of this graph. We have kind of a nice line. It dips down slightly but gently and rebounds, and then continues off toward positive infinity. So you could imagine possibly rolling a marble along that, or the illustration that I'll continually use is an ant. So imagine an ant walking from left to right. He kind of has a nice smooth walk. A bit of a dip, a bit of an incline, but a nice smooth walk, and it continues. There are no spots that he needs to jump. We will discuss this graph. Note that a graph is continuous if it has no jumps, breaks, or holes. So my example of the ant kind of demonstrates all of that, but in a more lifelike way, I suppose. You can draw a continuous graph, and your pencil never leaves the paper. So keep that in mind. Again, that's something that can be explained by the idea of a small object, or an ant, having a nice, smooth, and continuous stroll along the line. And finally, there is no value of x that makes the denominator 0. So considering our function itself, no matter what value we substitute for x, we will be squaring it. And so no matter what value of x we get, x squared plus 1 can never equal 0, as long as we're substituting in real valued numbers. Our second graph, note it's the graph of the binomials x plus 3 or times x plus 2 for a numerator over x plus 2 for a denominator. So note, the x plus 2's, those binomials would cancel one another out, and then we would just have the graph of y equals x plus 3. And you should recognize that's the straight line with a slope of 1 and a y-intercept of 3, which we can virtually see here on the graph below. The interesting thing about this graph is that when we substitute a negative 2 for x, negative 2 plus 2 is 0. That leads to a 0 denominator. And that age-old rule of math that says we cannot divide by 0 tells us that this function will not be defined at the value 0. That explains the hole in the function. It is discontinuous at that point. The graph is not defined there. If we go to the value negative 2 for x, or for our input, and we search up and down vertically, we won't hit the graph. It's not defined at that particular input value. It's defined everywhere else at, let's say, x equals negative 1.99999 infinitely, so infinitely close to negative 2. From both the positive side and from the negative side, our function is defined. But at precisely x equals negative 2, our function is undefined. So we can see that both graphically, by the hole in the function, the open dot, as I'll often refer to it, but also algebraically, by looking at the function itself and noting the denominator and what value of x makes that denominator 0. So considering some information below, note the arrows that tell us which of this mess of information leads to which graph. The graph has a hole at x equals negative 2. Seems like we already discussed that. And if x equals negative 2, the denominator will be 0, so x cannot be negative 2. Seems like we already discussed that as well. Good to repeat things. Good to make sure you have a good understanding. And we'll take a look at this graph on the right-hand side. Another discontinuous graph, this time at the value x equals positive 2. Note that at x equals positive 2, we would have a denominator of 0, violating that law. No denominators of 0. We can't divide by 0. So our graph will be undefined for x equals positive 2. Interestingly enough, that forms an asymptote, a vertical asymptote, one of those lines, in this case a vertical line, that our function gets infinitely nearer to, but will never touch. And also interesting is the fact that we have a horizontal asymptote here as well. So our graph will continually approach that horizontal line infinitely to the right and to the left, but never actually get to that horizontal value. A quick look at the information at the bottom to make sure I didn't miss anything. The graph jumps. Okay. And if x equals 2, the denominator will be 0, covered. So x cannot be 2. Point of discontinuity. If a is a real number for which the denominator of a rational function f of x is 0, then a is not in the domain of f of x. Poof, there it is again. x plus 3 over x minus 6. That's very convenient because we can use this, well, to be an example of what we're talking about here. So it says, if a is a real number, then a is not in the domain of f of x. F of x equals x plus 3 over x minus 6. So now, since a, well, for us again, a would be 6. 6 minus 6 is 0. A is a real number for which the denominator is 0. Then a is not in the domain. So again, the domain of f of x would be all real numbers except x equals 6. And how convenient. As soon as we're done with it, it leaves. Huh. The graph of f of x is not continuous at x equals a. And the function has a point of discontinuity at x equals a. A point of discontinuity can be removable or non-removable. A removable discontinuity is a point of discontinuity a of a function f that you can remove by redefining f at x equals a. Doing so fills in a hole in the graph of f with the point a f of a. So that seems really confusing. Perhaps, my gosh, it worked again. So I just had to think about it, and here's a graph for an example. A removable discontinuity is a point of discontinuity of a function f, so we'll let the orange graph represent our function f, that you can remove by redefining by redefining f at x equals a. So in this case, a will be the value -2, and it's as though this part of the function would just be redefined somewhere else. So let me just for a moment, how convenient that I'm using orange. So we'll say that at exactly this input value -2, we have redefined the output value of the function to be this point. It looks like that would be 3. So in this case, f of -2 equals 3. All right, so that doesn't match our function. This is just an example of how a removable discontinuity works. We could, if given this graph, we could just think of this dot as having moved somewhere else. It's just defined somewhere else. Often these will be represented with piecewise defined functions, but we'll see more on that in the future. Again, to get the most out of this example, it said doing so redefining f at x equals a, fills in a hole in the graph of f with the point a f of a. So that would be our x value or our input value, and this would be our output value or our y value. So potentially, notice this. If instead of defining f of -2 to equal 3, we were to define it as f of -2 equals 1, and watch out, all of a sudden, we can fill in that single point of discontinuity. And that is our definition of a removable discontinuity. A non-removable discontinuity, a non-removable discontinuity is a point of discontinuity a of a function f that is not removable. It represents a break in the graph of f where you cannot redefine f to make the graph continuous. So here's an example. We don't have one of those convenient spots where a chunk of the graph has just been taken out of place, or at least out of the place where we would expect it to be, as an object we're rolling along the line, or an ant we're marching along the line, possibly 1 by 1 or 2 by 2. I've heard that's the way ants march sometimes. Hurrah, hurrah. When you are looking for discontinuities, it is helpful to factor the numerator and denominator as a first step. The factors of the denominator will reveal the points of discontinuity. The discontinuity caused by x minus a to the n power in the denominator is removable if the numerator also has x minus a to the n power as a factor. Very much like one of the examples we saw on the last page, where I pointed out that, if I recall, x minus 2 could be canceled from both the numerator and denominator. And a quick peek back at that page reveals it was actually the x plus 2. So note, x plus 2 is in the numerator and denominator. Therefore, we would find a removable discontinuity, or a point of removable discontinuity, at the value that makes x plus 2 equal 0, which we know and have already discussed is negative 2. All right, so more on a point of discontinuity. The graph of y equals x plus 3 times x plus 2 over x plus 2 has a removable discontinuity at x equals negative 2. You can make the function continuous by redefining it in the following piecewise defined function. So our function y will equal x plus 3 times x plus 2 over x plus 2 if x does not equal negative 2. So basically meaning for all other real numbers, everywhere else on the graph, except exactly where x equals negative 2, we'll define the function this way. However, since our function is undefined at that value, x equals negative 2, we can peek at the graph to the right to verify the whole. We will define y to equal 1 if x equals negative 2. And that redefinition, or that second piece of our function, fills in the gap. And so that would be an example of making the function continuous by redefining it. And so what's really taking place here is that essentially this part of the graph, or the function, gives us this line with the hole in the middle, because when x equals negative 2, our function is undefined. This part of the graph would, if graphed, fill in the bubble to form a continuous function for us. One thing to keep in mind, concept, is that points take up no space. That hole really does take up space. It's a figure that we use to represent a concept, the concept of a point, which is a single point in space, which truly takes up no space. In theory, we should be able to zoom in on that point infinitely, and it would continue getting smaller and smaller, or appearing smaller and smaller. These graphs actually use pretty large open dots, but we just have to imagine that the point takes up no space, and if that single point were filled in, our function would then become continuous. And I say that because when I fill in this dot, it makes it look like a kind of an ugly, bumpy function, like a knot on a log. But truly, it should just be a perfectly filled in point, creating a nice smooth curve and a nice ramp for our ant to walk up, or in the winter to sled down. So ants do that as well, 2 by 2. So another note about a different kind of point of discontinuity, excuse me. This graph, which we've seen before, y equals x plus 4 over x minus 2, has a non-removable discontinuity at x equals 2. There is no way to redefine the function at 2 to make the function continuous. Let's try. Let's say that f of 2 equals, let's say f of 2 equals 0. Nope. That sure didn't make a nice, smooth, continuous curve. What if f of 2 equals... Oh, I see where they're going with this. That's heading toward positive infinity. What if f of 2 were positive infinity? So let's assume that I've placed this dot way out here at positive infinity. We'll pretend that was even a possibility. Remember, this line won't equal 2. 2 is a vertical asymptote, meaning this line will get infinitely close to this value, x equals 2, or this vertical line. It won't touch it. So even this doesn't work. That was just a lot of work, though. What if f of 2 is negative? Well, you get the idea. I don't think I need to do any more of these. No matter where we place the point or define f of 2, we will not arrive at a nice, smooth curve. And notice our ants. I mean, this guy, well, this is just not a good hike to go on. He's going to end up, we don't even want to talk about what happens to this ant as he's walking, and so anyhow, let's move on. Problem number 1, finding points of discontinuity. What are the domain and points of discontinuity of each rational function? Are the points of discontinuity removable or non-removable? What are the x and y intercepts? That's several things to figure out. Good thing we're good at this. A says y equals x plus 3 over x squared minus 4x plus 3. So our first step, as was mentioned before, a good idea is to factor our polynomials. So we take a look at the denominator. It's a factorable trinomial, and that doesn't take a lot of effort in order to factor that to become x minus 3 times x minus 1. All right, if you need a review of factoring, I'd encourage you to look up Khan Academy videos, see me for some example problems, or come in after school and we can discuss factoring in greater detail, because it's going to be a fundamental concept that you need to know, be familiar with, at least brushed up in a quick review, to make this section go more smoothly. So the function is undefined where x minus 3 equals 0, right? Because if x minus 3 equals 0, who cares what x minus 1 equals, because 0 times x minus 1 is going to equal 0. And anywhere where the other binomial in our denominator, x minus 1 equals 0. So these two values are 3 and 1. So when x equals 3, our function is undefined, right? Because that would lead to a 0 denominator. And where x equals 1, our function is undefined. Again, 0 denominator. The domain of the function is the set of all real numbers except x equals 1 and x equals 3. That was defined for us earlier. A rational function like this with a polynomial over a polynomial will have a domain of all real numbers except those real numbers that lead to a 0 denominator, and consequently also points of discontinuity. There are non-removable points of discontinuity at x equals 1 and x equals 3. Recall that in order to have a removable point of discontinuity, we would need at least one of our denominator binomials, so either x minus 3 or x minus 1, to also appear in the numerator. And that's just not the case in this problem. If we for a moment imagine that the numerator were x minus 3, then we would have a point of removable discontinuity at the value 3, right? X equals 3, because we would have the matching x minus 3 in the denominator and x minus 3 in the numerator. The x-intercept occurs where the numerator equals 0, right? Because the x-intercept is where y equals 0, and the y-intercept, and I'm talking generally about any function, the y-intercept is where x equals 0, or anywhere that x equals 0. So the x-intercept occurs where the numerator equals 0, because 0 divided by non-zero numbers is 0, and at x equals negative 3. Oh no, not and. Simply at x equals negative 3, because note, negative 3 plus 3 is 0 and leads to a 0 numerator, and hence a 0 y value. To find the y-intercept, much as we've done in the past, we just let x equal 0 and simplify. A little bit of work, substitute some values. Y equals 3 over 3, which we know is just plain old 1. B says y equals x minus 5 over x squared plus 1. Same directions. We have some things to identify, points of discontinuity, determine whether those are removable or non-removable, and intercepts, x and y intercepts. You cannot factor the numerator or the denominator. So this saves us a little bit of work. Although it's arguably fun work, like solving a puzzle. Anyway, also, there are no values of x that make the denominator 0. Think about it. X squared plus 1, negative times the negative is a positive, plus 1 wouldn't be 0. What if x is positive? 3 squared would be like 9. 9 plus... Nope, so they're right. The domain of the function is all real numbers, and there are no discontinuities. Well, we weren't only asked about discontinuity, so the x-intercept occurs where the numerator equals 0. That's at x equals 5. Think about it. What minus 5 is 0? 5 minus 5 is 0. I feel like an episode of Dora for a moment. To find the y-intercept, we let x equal 0. Some substitution, some simplifying, a quick reduction. Negative 5. Fantastic. C. y equals x squared minus 3x minus 4 over x minus 4. Looks like a possibly factorable numerator. Yep. And the directions say factor the numerator and denominator. Yeah, we don't really factor the denominator, but we at least take a look at it. Factoring the numerator, we find x minus 4 times x minus 1, and lo and behold, x minus 4 appears in both the numerator and denominator. Do you remember what that means? I do. The function is defined where x minus 4 is undefined, where x minus 4 equals 0. That's at x equals 4. Note, because that's the value that when substituted gives us a denominator of 0. That's just a huge key concept. Remember that. You're looking for the values of x that make the denominator equal 0 if you're looking for points of discontinuity. The domain of the function is the set of all real numbers except x equals 4. We've heard that over and over. Because y equals x plus 1 except at x equals 4, note if we were to look at the original function and cancel out x minus 4 and x minus 4, we're left with simply y equals x plus 1, that nice straight line, slope of 1, y-intercept of 1. But we have this point, this removable discontinuity at x equals 4. So that's represented with an open dot, or a hole, at the point where x equals 4. We could redefine the function to remove the discontinuity, or fill in the hole. In this way, with a piecewise defined function where y equals the top stuff if x doesn't equal 4, right? Because if x equals 4, that top stuff just doesn't work. And where it equals 5 if x does equal 4. The x-intercept, so moving on to the x-intercept, we've already defined our removable discontinuity. The x-intercept occurs where the numerator equals 0. So what values make the numerator equal 0? Well, -1 makes the numerator equal 0. We could also take a look at our graph to identify that information. And to find the y-intercept, of course, we let x equal 0 once more, and then simplify. Y equals 1. And now is your chance to show that you have got it. What are the domain and points of discontinuity of the rational function? Are the points of discontinuity removable or non-removable? What are the x and y-intercepts of the rational function? First, part A. Second, part B. And third, part C.